Greetings, everyone. Welcome to Love, Laugh, and Learn. I'm Dr. Eason, and I've got a question for you. What do Albert Einstein, ancient Americans known as the Mayans, and quartz crystal all have in common? Answer: they all play a role in the historic developments of how humans have come to understand the concepts of space and time. And that's the topic of today's video. We're going to be discussing what exactly is space and time from a more scientific perspective, because we got to be a little bit more precise. And maybe an even more important question is, what do we stand to gain by getting the answers to questions like this? All right. So if that sounds interesting to you, well, you might want to stick around. All right, so let's get to it. Let's first talk about the concept of space. And what is space exactly, right? So let's say, hypothetically speaking, let's say you and I were somewhere and just happened to be a friendly alien spaceship happened to land right in front of us. And this friendly alien gets out of the vehicle and comes right over to us and starts to speak to us. And it sounds a little something like this. Of course, that's my impression of how the alien speaks, because, I mean, we all know that's exactly how an alien sounds, but I digress. Okay, so the alien is basically asking us, after the translation, friend, what is space? Can you please explain it to me so I can understand what this is in the human mind? What would you tell the alien? All right, so let's give some thought to how would you describe space to someone who knows nothing about space, but they living in the same space as you. All right, so maybe we'll do a little something like this. All right, so we got to describe two things when we describe space. So we got to describe both the position x, but we also got to describe the change of position x. To describe just x, all I need is a real number line. I could take any object, put it at x. But because I have to describe changes in x, I got to be able to say whether I go plus or minus. So we need a plus x, and we also need a minus x. And this gives us a way to describe any one-dimensional space. All right, so 1D space, there we go. All right, so now we can extend this idea and go a little bit further, but notice that we got to be able to transition between positive and negative numbers. So that transition point we call the origin. That's kind of like the zero of the real number line. All right, we can take this idea and extend it and add another axis perpendicular or 90 degrees from our first one and do exactly as we did before. Now, when we do this, notice now we're not limited to one line. Now we can take a point in this two-dimensional space, and any point I draw there, I can actually represent it as a combination of both this horizontal line and my vertical axis line. Let's take another point over here. I can do the same thing. And now we have a complete description of 2D space. All right. Oh, and let's not forget, we also got to add a description of plus and minus. And we call this, let's say, y. So we got a plus y, and we also have a minus y. Okay, so now we got a two-dimensional space, so we can extend this further, because if you were to look from the right side, you would see that this cross looks like a line. So we can add a third axis, a third dimension to fully describe our space. And that we typically call z. We got to get two arrows, and we got to give it, say, a plus z. And then we also can give it a minus z. And this gives us a full description of what we call 3D space. And now we can tell our alien friend, hey, this is 3D space. Okay, so we have managed to provide some description to our friend, something that describes space. And we might say this 3D space. We've used three dimensions in order to describe what we call space. And of course, when you do something like this, the question will inevitably come up as to whether this is enough to describe all of our spatial experiences. And of course, the short answer to that is going to be no. And the reason is because of the little requirement with our dimensions. If you recall, when we write out a single dimension, we not only need to be able to express a single point x or y or z, but we also need to be able to express a change in that. So a delta x, delta y, delta z. It's the delta x, delta y, delta z, which imposes the requirement for both positive and negative numbers. And so we end up with an axis that can go either left or right, and we've got now a transition point in the middle, which we call the origin. We tend to call the origin. And so that point is necessitated out of the requirement that we need to be able to express not only x, but changes in x. And that, of course, true for all three dimensions. So it becomes evident at some point that because of this delta x requirement, this opens the door to being able to start observing, and of course this is what would take place experimentally, is that this opens the door for us to start observing that one could not make changes in that what we call, that, let's say, your position, x or y or z, or that 3D point, without also making changes in a variable or parameter that we call time. So this means that we cannot produce in physical reality a delta x that is finite, some value of delta x, without also producing a finite value in delta t, or a change in what we call time. And this has ramifications, because if you think about it, if I were able to produce a change in x without a change in time, so that would mean that I could create a delta x is equal to some finite number, and a delta t could be equal to 0. And that would mean that I could create a velocity, which is given or derived from delta x divided by delta t, that is infinite. So I can have delta x over delta t, which would be equivalent to dividing by 0, because we can produce, hypothetically speaking, in this argument, if I can produce a change in position while at the same time doing it in 0 amount of time, then of course that gives rise to infinite velocities. And of course, not only have we never seen this, it turns out that it's not really even remotely possible as far as everything that we've ever seen, both physically, experimentally, as well as theoretically. So this opens the door now to us having to start to consider this concept or this notion of what we call time a little bit more seriously, because there's a very close connection between what we call time and these other parameters. And like we just said, there are some limitations on creating changes in position, and it dictates certain things that will be true also for this other variable or parameter that we call time. All right. So it was not until around the late 1800s that we began to really make some significant progress along trying to understand this. This was well after several scientists had already made successful measurements of how fast, for example, speed of light moves. So by knowing that the speed of light is finite, it's not infinite, while at the same time recognizing that light is composed of massless constituents, which we call photons. So photons are massless, yet even a massless particle does not have an infinite velocity. It still has a finite speed. So delta x over delta t is still a finite number, even for a body with no mass. So it stands to reason that a body that has mass will not move faster than such a body without mass, which we call light. And so this behavior of light, which was becoming more well understood towards the end of the 18th century, or 19th century, started to give some insight into the relationship between position and time, and also kind of these fundamental limitations on motion and how fast a physical body can move, because it's not necessarily obvious that there's a limitation to how fast things can move in our universe. All right, but the information and observations of this were starting to unfold around this time. All right, so if we now have to open the conversation up to start discussing this concept of time. So what is time? All right, so we've kind of tried to make some progress with explaining what space is, but now we want to segue a little bit and talk about what time is. So again, our friend is here in front of us, and we have to, kind of explain. Okay, so we've basically started to understand that it's not really enough to just use X, Y, and Z to explain our physical experience in the world, and in particular space. This spatial configuration, which we're a part of, requires the inclusion of a parameter known as time. And that's because it's a part of motion, a description of motion. So you have position, but you also have changes in position, and that's where things like motion come into the picture. Things like velocity, acceleration, and so on, right? So we know a little bit about time. We know historically that we've always had methods that we've used in order to denote what we call time. You might have heard of the ancient Americans known as the Mayans, who gave us calendars, including both lunar calendars as well as solar calendars. And what do these calendars do? They basically use rotating bodies that have some frequency of rotation, and we measure essentially how many of those rotations have elapsed. And we count based on those. And so while this may on one hand seem pretty simple, on the other hand, it's really intriguing and interesting and kind of profound, because what this is indicating is that time is tied not only to motion, but to some kind of harmonic motion, some type of periodic motion. And, I won't get into this, but we know from quantum mechanics, for example, that all bodies are associated with harmonic frequencies. Quantum the energies actually are proportional to these frequencies. And so it's very interesting when you start to point out that time is tied to frequencies and energy is tied to time. And so you start to uncover relationships, for example, in quantum physics, that tells us there are relationships between things like changes in energy and changes in time. And this is underlying those relationships. So we can't have motion in the universe without it being tied to some kind of motion, right? So and not only just motion, periodic motion. So every method that you've ever seen that measures time, whether we're using the sun or we're using the moon, or even if you look at a modern device like a computer, it's using a quartz oscillator or some type of special material which can be designed by cutting it in a special shape and size to tune its frequency. And by putting it in some kind of electrical circuit, you can drive it into very stable oscillations, which are absolutely equivalent to the oscillations of the sun or the oscillations of the solar system and the oscillations of the lunar system. All right. So all of these types of systems and mechanisms have to be used in order to measure what we call time. And again, we're just really tracing this back to the fact that I cannot make a change in my position without also making a change in time. So this is a very interesting kind of connection that's starting to, be identified around this time. So what was kind of the progression that really unfolded led to the point of looking at different reference frames. So for example, say I'm standing on the ground and I'm at a train station, and you might think of the person standing on the ground as one reference frame. And the person or a person standing on the train or the train itself, which is moving at some finite velocity, also can be considered another reference frame. And what was some very strange observations were starting to take place around the end of the late 1800s. So, and this had to do with studying light. So we know light moves pretty quickly, but it doesn't move infinitely quickly. So it has a finite speed, which happens to be around 3 times 10 to the 8. Meters per second, which is a pretty large number. So that's 300 million meters per second. That's the speed of light. And it's never been observed that light can go faster than that. So that means that if I have a light source on the ground of my train station and I set the light to be emitted and travel relative to the ground, that reference frame where this person is sitting or is standing, then the light is going to travel at, let's say, a speed which we denote typically by a letter C. All right, but that number 3 times 10 to the 8 meters per second. So that person that emits the light at in that reference frame will observe speed around that value. Now, you might think, based on intuition, that if you were to put the light source on something that's moving, that you can then create an additional component of speed to the light, to the photons in the light. And if you were standing on the side of the train and you were to do some kind of detection of the light that is coming out of a source that is on the moving train, you might think that you're going to measure speed of light to be faster than what you would measure on the ground, because that's what our intuition tells us, because that would happen if I had a Nerf ball and I was threw the Nerf ball with a certain amount of force on the ground, it would move at a certain velocity. But obviously, if I'm riding the train and I do exactly the same, exert the same force on this Nerf ball while I'm also on the train, the person standing on the ground will experience a much larger velocity in terms of, when they receive the Nerf ball from me being on a moving train, as opposed to me being on the ground. So this type of experience by intuition is what you would expect if you were putting anything on a moving source, or putting the source on a moving reference frame. And so what was starting to be observed was a very strange thing, and that is that you do not see light to go faster and faster and faster by putting it on faster or putting it on moving sources. You instead measure the same speed of light. So light appears to be limited on how fast it can move, whether it's in a stationary frame or a moving frame. And these are some of the early observations which are becoming very evident, looking at how light moves, for example, with sources in water and so on. So these types of experiments started making scientists scratch their heads a little bit, because, again, this is counterintuitive based on our everyday experience. And so a very bright scientist comes along by the name of Lorentz and starts to look at this theoretically and make the assumptions that are consistent with those observations. If I were to assume that the speed of light was the same in both of these reference frames, the moving reference frame as well as the stationary frame, what would be the consequences? And one of the things that was found was relationships between positions in space in one frame, say the person standing on the ground, and positions in space in the moving frame, say the person standing on the train. And this also, the relationships between these two frames also involve this component that we call time. And so you must include the motion of that reference frame as well as the component what we call time. And when you do that, you can get a description of 4 variables that appear to describe our spatial experience. Again, we see that it's not just X, Y, and Z, but we now have a component of time, which, just like X, Y, and Z will be a function of X in one frame, will be a function of X in the other frame, plus a function of time. And it turns out that time, when Lorentz worked out his what we call Lorentz transformation, what he found that just like X, Y, and Z, time also becomes a function of space as well as time in the other reference frame. There's some pretty way out stuff. So I hope that, hopefully if you're scratching your head, it's for the right reasons. But we're trying to just kind of move us in the direction of trying to understand how deep and profound it actually is to actually ask the question, what is space and time? Because the simple requirement of any coordinate system to be able to describe changes in X opens the window to require us to describe time, and in particular changes in time. And this is how we can obtain things like velocity, acceleration, so on and so forth. All right. So this is where this ends up heading. So thanks to people like the Mayans and thanks to technology, we know how to describe time, but it's extremely interesting that we can't actually ignore time in our description of space in the way that it's observed in our own experiences. We must also include this thing we call time. All right. So this is the idea. And another interesting thing that follows from things like the Lorentz transformation, which, again, this is part of what is almost like the foundation of what's known as the theory of relativity, is things like this Lorentz transformation, which started to look at things that happen when you assume that the speed of light is limited to c, which is 3 times 10 to the 8. And you can't find another reference frame that will have a higher speed than that. It will always be the same in all of the different reference frames. All right. So these are consequences from that. And what Albert Einstein, the well-known scientist, started to do, which was kind of monumental, was take a look at the effects of that on physical systems, the laws of physics that describes these systems. He started with something simple like velocity, and he derived something that's known as the velocity addition formula. And then you look at how that affects energies, and you probably have heard of E equals mc squared, but E equals mc squared is only possible because of the Lorentz transformations and because of looking at a particular, these relationships that fall out as a result of this assumption about light. Okay, so this is where we're going, and this is what this means in terms of space and time. We have to understand that we can't actually have a complete description of space without including our description of time. But when we do that, kind of an entire universe of new pieces of information start to open up. And that's where the theory of relativity and all of its consequences come into play. All right, so that's really what I want to make sure you understand about this question of what is space and time. We understand that it's something that describes the what's around us, what we exist within, but it's also important to understand that it has a very intimate connection with time, and that connection necessitates things like finite velocities. No matter what the physical system is in the universe, it can't go faster. It can't go at an infinite speed. It can, and that just is another way of saying that creating a change in position will always correspond to a finite change in time. All right, so I hope that makes sense, and I hope that you have come to some understanding of what it means when we talk about space and time. And really one of the takeaways I want to make sure gets imprinted on your mind is that little subtle thing with this changes in space. That is what leads to a two-directional axis that requires these positive and negative numbers. And because of being able to describe changes in space, opens the door for us to include descriptions of time. And once we combine all those things together, we actually land at a place with the Lorentz transformations and the special theory of relativity and a whole slew of new ways of improving the description of physical systems in the universe. All right. So that's it. That is exactly what space and time, at least in a kind of a nutshell kind of way. All right. So I hope that makes sense and gives you a little bit of insight of what space and time is and what their relationship, might be. And if you have any questions, feel free to drop, some comments under questions in the box below. You know the routine. So, all right. So that's it. And we'll see you guys later. Thanks for watching. Bye.